Hello friends, in this video we are going to discuss that how a BJT changes its operation of region automatically. So far we have seen that a BJT has three region of operation depending on the JE and JC junction biasing. So these are the JE junction if it is the emitter region, it is the base region, and it is the collector terminal. So this PN junction is the JC junction. This is the JE and the JC junction. So depending on the biasing of JE and JC, the transistor operates in three different regions. That is the cut-off region. Second one, the active region, and the third one is the saturation region. Now, if we make the JE junction reverse bias, and if we make the JC junction also reverse bias, in this case the BJT will operate in the cutoff. Similarly, if the emitter junction is in the forward bias and the collector junction is in the reverse bias, then the BJT will operate in the active region. And last of all, if the emitter junction is in the forward bias connection and the collector junction JC is in the forward bias connection, then the bipolar junction transistor operate in the saturation region. So we have taken here a NPN transistor and we've seen that this is the J junction and JC junction. So this is a block diagram of an NPN transistor. Now we know that for an NPN transistor, the circuit symbol of an NPN transistor will look like this. So this is then emitter terminal, and here it will be a collector terminal, and here it will be the base terminal. So let us discuss this change of operation with respect to a circuit. The circuit looks like this, where it is an N transistor. This is the emitter, this is the collector, and this is the base terminal. So to make the JE junction, so here in this case there will be the JE junction, and here there will be the JC junction. To make the JE junction forward bias, we have given a voltage like this, VBB, that is the base voltage, and we have connected a resistance at the base, that is the base resistance. We change this VBB. Similarly, at the collector terminal, we have connected a resistor RC. We have given a voltage. Now, let us assume some values that the VCC value is 10 volts, suppose, and the RC value, suppose it is 5 kilo ohm, and the RB value is, suppose we have taken some value of RB. Now, if we apply the KVL, so before applying the KVL, we can see that this voltage here plus and the voltage at the emitter, so the voltage between the base and the emitter can be written as base to emitter. Similarly, the voltage at the collector and the voltage at the emitter can be written as PCE voltage. and the voltage between the collector and the base written as VCB voltage. So due to this VBB, no, some amount of current will flow into the base terminal, and there will be some amount of current that will flow into the collector terminal, and current will go out of the emitter terminal. Now, if we apply a KVL in the input loop, the input loop looks like this. So if we apply the KVL in this input circuit, so we can say that the input KVL equation will be minus of VBB plus IB into RB plus PBE equals to 0. From this equation, we can find the value of PBB is equals to IB into RB plus PBE. So this is the first equation that I will get from the input circuit KVL. I am denoting it as equation number 1. Now, we also know that the IC current can also be written as beta into IB, because right now we have applied a voltage at VCC and VBB in such a way that the JC and the JE junction are forward. JC is the reverse bias right now and JE is the forward bias. So right now it is in the active region. So in the active region we can say that the IC current will be equals to beta in AB. In the third case, if we apply a KVL, so if we apply a KVL in the output circuit, so the output circuit will look like this. So this is the output circuit. We can say the output circuit. If we apply KVL, then it will look like this: that minus of VCC plus IC into RC plus PCE is equals to 0. So from this equation we can find the value of collector to emitter voltage, that will be equals to PCC minus IC into RC. So we can name this equation as the equation number, which can be found by applying KVL in the output circuit. In the fourth way, we can say that the if we find the voltages around the transistor, then it can be written that the collector to emitter voltage will be equals to the collector to base voltage plus the base to emitter voltage. So this is another equation. These are the voltages across the transistor terminals. So let us denote this equation as the fourth equation. These are the fourth equation that we have found on the right now. So for the first case, what we are doing, so for the first case, we will make this VBB voltage 0. So the case 1 can be written in this form. In the case 1, what we are doing, that if the VBB voltage is equals to 0 volt, So we'll see what will happen in this case. So here right now the VBB voltage is volt. Since the VBB voltage will be 0, so we can say that the base to emitter voltage, that this one, this voltage will also be 0 because we have applied a 0 voltage. So we can say the base to emitter voltage is 0. For this case, we can say that since the VBB voltage equals to 0 volt, so we can say base to emitter voltage will be equals to 0 volt. And since the VBE voltage is 0, we can say that the current is base terminal will also be 0. That's why the IB will also be. So due to the application of 0 voltage at the VBB, so we can see that 0 base current we have got. Since the IB current is 0, so at the collector terminal, we can say that the collector current, that is IC will also be equals to 0 because the IC is equals to beta into IB. So beta value is 0. So beta value is there, but the IB value is 0 ultimately. So hence we can see that we have found that the IC current is also 0. Now from the fourth equation, we have seen that VCE value, we have found that the VCE is equals to VCC minus IC into RC. This is the fourth equation. The third equation. The third equation is VCC minus ICRC. So if we put all the values here, IC is equals to 0. So we can say that VCE equals to VCC, and we have taken that this VCC voltage as 10 volt, so get it as 10 volt. So we can say that the collector to emitter voltage is now 10 volt when the VBB voltage is 0 volt. So here we can say that the collector to emitter voltage as, that is VCE, as 10 volt. This was the RC resistance and it is 5 kilo. So, and it was my RB resistance. So we have seen that the VCE is 10 volt. Since the VCE is 10 volt, so we can say from the fourth equation that we have derived earlier in this video that VCE is equals to collector to base voltage plus base to emitter voltage. Collector to emitter voltage is equals to 10 volt, and here it is VCB and VBB is equals to 0 volt. So from this equation we can find the collector to base voltage as 10 volt. We have found that the collector to base voltage as 10 volt also. Since the VCB is 10 volt, so we can say that the collector is at higher potential than the base, and this is my N transistor. So here it is the JC junction, and this JC junction is now at reverse bias. So we have found that due to the application of the zero voltage at the VBB, my collector junction has turned into a reverse bias condition, and my VBE is the base to emitter potential is also 0 volt. We have already found that. So from this voltage value we can say that the JE junction at this point, JE junction will be also reverse bias. So we can say that due to the application of zero voltage at VDB, the JC junction is turned into reverse bias as well as JE also turned into reverse bias. So right now the transistor, that is the BJT, is in cutoff region of operation. And in this cutoff region, we can draw the equivalent circuit like this. This is my collector, this is my base, this is my emitter. So emitter, collector and base. So there is a connection of resistor RB here, and there is a zero potential applied here, and with the collector there is a RC resistance connected, and there is also a VCC connected here, and this is my VCC, that is the 10 volt, RC, RB, and VBB voltage equals to 0. So we can say that here the IC current equals to 0, the IB current is also equals to 0, and IE current equals to 0. But the VCE voltage right now is equals to 10 volt. Now the transistor is in the cutoff region due to the application of VBB is equal. After this, what we do, we will change this potential and increase this VBB voltage to some finite value. So let us take that right now we increase the VBB potential to some finite value. Let us assume that we have applied that the VBB as 1 volt. So what will happen when we increase the VBB voltage to 1 volt? So in the case 2, what we have done, we have made the VBB voltage 1 volt, which was 0 volt earlier in the case 1. Now we have applied here a 1 volt, and this is my RB. This is the RC value which is taken as 5 kilo ohm. This is the VCC which have taken 10 volt. This is the collector, this is the base, this is the emitter. This potential right now V VE, and this potential is right now the VC, and some amount of current flowing into the collector is IC, and some current is flowing into the base, that is IP, and there will be a current IE here. Since we have given the VBB equals to 1 volt, so we can say right now that is the base to emitter potential, which was 0 earlier, will be increased to some value. Let us assume that now the value is 0.6 volt. Due to this VBE 0.6 volt, we will get some amount of current in the IB. So IB will be 1 micro ampere. We have got a value of base current. So my IC current will be beta into IB. And let us assume the value of beta as 100 into 1 microampere will give 100 microampere. So from the equation of VCE, we can find the value as VCC minus IC into RC. VCC value is 10 volt, IC value is 100 microampere into RC value is 5 kilo. So after calculating the VCE, we will get VCE as 9.5, which is a positive value. That means collector is at higher potential than the emitter. So we have got the VCE value as 9.5 volt. Since VCE is 9.5 volt, so we can also find the value of VCE as VCE minus VBE. VCE value is 9.5 and VBE value is 0.6. So it will be 8.9 volt. We have got the value of VCB as 8.9 volt. So the collector is at higher potential than the base. So we can say that the JC junction right now in the reverse bias condition. And since the VBE potential is 0.6 volt, from this we can say that the base is at higher potential than emitter. So the emitter junction will be at the forward bias. So we can see when we have made the VBB equals to 1 volt, JC has turned to reverse bias and JE has turned to forward bias. That means that right now the transistor is operating the active region of. So in the active region of operation, we can find the equivalent circuit of this transistor like this. The transistor part will be replaced by a diode and dependent current source circuit in this format. So if this is the collector terminal, the collector junction can be replaced by this current dependent source and it will be beta into IB and there will be a diode at the JE junction and this is the emitter. So this is the collector and here it will be a base. So there will be a resistor connected with the base. It will be like this. This is the RB resistor in which there will be a VBB voltage source connected and we have applied the VBB as 1 volt and with the collector there will be a RC resistor and a VCC. So there will be a VCC connection and VCC 10 volt, RC value was 5. This is the equivalent circuit of the transistor when we have given a voltage VBB as 1 volt. Now what we have seen here that since we have increased the voltage of VBB, so the base to emitter potential has been increased and with that the IB current has also increased. Since the IB current has increased, the IC current has also been increased. Since the IC current has increased, the VC potential has decreased. This will be the conclusion of this case when the VBB potential will be increased. Now let us increase the VBB potential further. So in the case 3, what we will do, we will make the VBB potential volt. So here it is the VBB potential and it is 2 volt. This is the RB resistance. This is the RC resistance that was 5 kilo ohm, and here it is VCC that was 10 volt. So this is the collector, this is the base terminal, and this is the emitter. Now what is VBB? Let us assume that right now, since we have given the VBB is equals to 2 volt, that we have increased the VBB. So previously the VBE was 0.6. Right now the base to emitter potential will be also increased. So it will be increased to 0.7. And the base current will be 10 microampere. Previously it was 1 microampere where the VBB was 1 volt. So we will get the IC current as beta into IB. Beta value is 100, IB is 10 microampere. So we can calculate the value of IC and it will come out as 1 milliampere. From this equation, we can also find the value of VCE, and VCE will be VCC minus IC into RC. VCC value is 10 volt, IC value is 1 milliampere, and RC value is 5 kilo ohm. So we will get that VCE value will be 5 volt. Previously it was 8.9 volt, so it has been decreased to 5 due to the application of 2 volt at VBB. So from VCE we can calculate the VCB. So VCB value right now will be 5 volt, that is VCE value minus the VBE value, and VBE value is 0.7 volt. So we can say that the VCB value will be 4.3 volt, which is a positive value. Collector is at higher potential than the base, so we can say that the JC junction will be, and since the PBE is 0.7 volt, so we can say that the JE junction will be at forward bias. Till now the transistor is in the active region of operation. Now if we give the PBB as, that means if we still further increase this PBB, and if we give the VBB voltage as 3 volt, let us see what will happen. In the case 4, we have given a voltage VBB as, since we have given VBB as 3 volt, so we can say right now the base to emitter potential will increase and it will go to a maximum value VBE max, and the VBE max value is of the order of 0.8 for every transistor generated. So since VBE will be at maximum value and the collector to emitter voltage will be at a minimum value, that is VCE, because VCE decreases with the VBE increment. So the minimum voltage that can happen at the VCE is 0.2 volt. So we can say that the VCE value is equals to 0.2 volt. So from this we can calculate the collector to base potential. The collector to base potential will be equals to the VCE potential minus the VBE potential, and we can see the VCE is zero point 0.2 and VBE is 0.8 volt, so we'll get minus 0.6. So we can see the collector to base potential is right now negative. That means collector is at lower potential than the base. We can say that the JC junction will be right now in the forward bias. And since the VBE, that is the base to emitter potential, positive also here, so we can say that the JE junction is right now also in the forward bias. For this case, the transistor is right now operating in the saturation. So the transistor is now in the saturation region, and in the saturation region we can see that the VBE value will be the maximum value of the base to emitter voltage. So it will be, you can say that in saturation the base to emitter potential will be maximum and the collector to emitter potential will be minimum, and the IC current will have a maximum value and the base current will also have a maximum value. So we can say that the IC maximum can be found from this equation VCC minus VCE minimum divided by the RC. We have seen that VCC is 10 volt, VC minimum 0.2 volt, RC is 5 kilo ohm. If we calculate, then we will get 1.96 milliampere. So we can say that right now the transistor is in the saturation, and in saturation we will get this type of potential and this type of current. Beyond saturation, that means if we increase further of BBB, that is beyond saturation, the IC current, that is the IC current at saturation, is always less than the beta IB. So we can say that IC sat will be less than beta IB in the saturation region. This is how the transistor changes its operation in automatically due to the application of different VBB voltage. So if we conclude the whole cases in a single circuit, then it will look like this. Start. So this was our circuit. So we can say if we write the conclusion of all the cases, then the conclusion will look like this. At first, when the VBB potential was 0 volt, then the VCE or the VCB voltage, if we write like this, that the VCB voltage was plus minus, or we can say like this, plus minus 10 volt, and the base to emitter potential was 0 volt. That's why the JC junction here, JC junction was at this point, the JC junction, that is the collector junction, was at reverse bias, and the emitter junction here was also at the reverse bias. Now we have changed the potential of VBB 1 volt. When we have changed the potential to 1 volt, the VCB value has been decreased and it was 8.9 volt, and the VB potential has increased. The value was 0.6 volt. That's why the transistor has gone to the active region, and after that, after 1 volt, we have given the VB value as 2 volt. At that case, the VCB value was like this. It was 4.3 and the VB value was 0.7 volt. So the transistor was in the active region, and after that we have given the value of VBB as 3 volt. That's why the VCB value has changed negative 0.6 volt, and here the voltage was VBE was zero point 0.8. That's why the JC junction is now forward bias and JE junction is also a bias, so it is in the saturation. And at saturation, this VCE potential at saturation was minimum, that is 0.2 volt, and in saturation the IC current was flowing, and this IC current was less than beta into IB. So we can say in this case the transistor was at cutoff. In these two cases, the transistor was in the active, and in this case, the transistor was in the saturation. So this is how the transistor automatically changes the region of operation depending on this base voltage that we have applied externally. Thank you.